So these are the last videos, part 2 of the exponential growth and decay problems. So you did graphing before, now we're going to actually apply it to word problems. Okay, so exponential growth can be modeled when a real-life situation increases by a fixed percentage each year. That's exactly what exponential growth is. Okay, so the example I gave before was thinking about money in your bank account. You have a set income, or what is it called? Interest rate. Sorry for that mind blank right there. You have a set interest rate where your money is going up by a fixed percentage each year, okay, your interest. So we model this as y equals a times 1 plus r to the t power. Let's define those. Y is our quantity after t years, a is the initial amount, just like in our general form, and r is the percent increased as a decimal, so increases by 1% would be 0.01. Okay, exponential, the same thing. The only difference is that we have a minus sign here. Up in exponential growth, we had a positive sign, a plus sign. So same concepts though. Alright, let's try to apply these into a couple of problems. Okay. So the population of the United States was this 248,718,301 in 1990. It was projected to grow at a rate of about 8% per decade. So it's saying this is a fixed rate, 8% per decade. Okay. First thing we want to do is predict the population to the nearest 100,000 for the years 2010 and 2025. So we're starting with 1990. So first, find the growth factor. So remember that growth factor is the R. So think about what R is. Well, we would have 1 plus R. Our R is 0.08. So that's how much we're growing by, is the 0.08 per decade. So we add that to 1 and we get 1.08. Now the expression for the population n, decades after 1990, we're just going to plug in the values. So A, remember, is our starting value. So we have y is equal to a, we plug in that value. Then we have 1 plus r, that's the 1.08, and then we have t. Okay, so fairly simple so far, right? It's just identifying what are the important features. And now we want to find the population for the years 2010 and 2025. So to do that, you just have to identify what is t. So in the year 2010, for example, that would have been 2 decades after. So our t would be 2. So plug in 2 and see what you get. For the year 2025, if you subtract 2025 minus 1990, you get, that was what? 3.5 decades. So plug those in for t and solve, and you should get the following. So you can see that the population grew quite a bit. Okay, alright. So that's example 1. Example 2. The rate at which caffeine is eliminated from the bloodstream of an adult is about 15% per hour. An adult drinks a caffeinated soda and the caffeine in his bloodstream reaches a peak level of 30 milligrams. Predict the amount to the nearest tenth of caffeine remaining 1 hour after the peak level and 4 hours after the peak level. So first, find that decay factor. Now, since it's decay, if we look back up here, instead of having 1 plus r, we have 1 minus r. So our r is that percentage decrease, which is 15%. So we're going to take 1, subtract 0.15, and we get 0.85. Now let's write our expression for the caffeine level, x hours after the peak level. Well, we plug in our initial value, a, which was 30 milligrams. So we have y equals 30. Then we multiply it by 1 minus r to the t, right? Or to the x in this case. So we have times 0.85 to the x power. And I typed it out here. I didn't write it. Now we just have to plug in x equals 1 and x equals 4 and solve. So go ahead and do those. And you should have gotten 25 milligrams and 15.7 milligrams. Alright, so I'm just going to leave the video at that, going through these 2 examples. Go ahead and make sure to finish example 3 and then also do these practice problems. So you'll know that you understand exponential growth and decay if you can do all of these problems, okay? And you can check your answers using the answer key that is posted on Blackboard. Great job today with this lesson.